Kitty, why are you so mad all the time, huh? Why are you so mad all the time? Oh, you're mad? Mwah. Um, if you're like taking Calc 3 class, it's like so hard. The part at the end is so hard. You got to parameterize everything. There's like a million different steps to every problem. And then you get to Green's theorem and it feels like some cruel joke. It's like, oh, now all of a sudden this is like the easiest problem I've ever done. So like, I mean, it's supposed to be that way. I mean, that's the point of the like fundamental theorem of calculus, is it's supposed to make things easier. So, you know, if you're waiting for the other shoe to drop on Green's theorem, there is no other shoe. That's it. It is easy. So here is Green's theorem. The main thing that you need to keep in mind when you're solving line integral problems is whether or not the line integral is enclosing a region. You know, so if your path starts and ends at the same place, then you can use Green's theorem. But if your path just starts at one place and then stops at someplace else, then you can't use Green's theorem. The other thing that you always have to check before you use Green's theorem is that your vector valued function has continuous partial derivatives. I know that I myself have failed to check that. I remember one time I was getting like crazy results. I was like, oh, it's all zero all the time. And then I was, oh yeah, you know, it didn't seem right. And it wasn't, because I was using the theorem when I wasn't allowed to. So, I mean, I don't think anybody's going to try to like trick you like in a classroom setting and, you know, throw you a problem where the function doesn't have continuous partial derivatives. But I'm just saying, we're all grown-ups here. Make sure that you check the assumptions before you use a theorem. This actual statement of Green's theorem is a relationship between line integrals and double integrals. Hopefully you can see this first line integral right there is the projection onto the normal vector. So that makes this one the flux. I would also call it the normal form. And this one is the projection of the vector valued function onto the tangent vector. So I would usually call this the tangential form or the flow. And the relationship is flux corresponds with this, which hopefully you can see as the divergence of the vector field. And flow corresponds with this one, which hopefully you can see as the curl, technically the kth component of curl. And I just want to point out here, if you use the theorem in this direction, then it really does make the problem easier, because on the left-hand side over here, I have line integrals, and that's like a complicated thing, right? You have to parameterize the curve. You got to make sure you're going counterclockwise, come up with your parameterization, plug all that into the differential form, and then do antiderivatives. On the right-hand side, we have double integrals, and double integrals are really easy to set up, right? You just pick an order, you draw a line, where it enters, where it exits. And then also the thing that goes on the inside of these integrals, those are like partial derivatives of the function. So, you know, a lot of times if you have like polynomial functions, then the partial derivatives make it a lot more simple. So, you know, from the student point of view, Green's theorem really does take problems that could be like a lot of steps and a real chore and makes them really pretty easy. Okay, so I've got a pretty classic flux problem set up here. First of all, this is the path that we're talking about here, and I've drawn the little arrows to indicate that we are moving around this in the counterclockwise direction there. And we're trying to find the flux of this vector valued function. And you can just check really fast. I mean, there's no problem. This is all just like polynomial. So all these partial derivatives are going to be continuous. So we're not going to have any issues at all. And then, so I've graphed it in CalcPlot 3D. So all I did was I inserted a vector valued function and I copied over the function from the problem. And then I parameterized the curve just to get CalcPlot 3D to solve it. But like the whole point of Green's theorem is that we don't have to parameterize the curve. So this is what we're dealing with here. And so to me, it looks like, you know, we've got some vectors flowing into the region on this side, and then we've also got some vectors flowing out of the region on that side. And as we go around, not the vector valued function is neither really, at a lot of times it's really perpendicular. Like right here, it's really perpendicular. I guess if I was moving along this red path right there, hopefully you can see my mouse, it does look to me like I would be going a little bit against the grain. So right at that spot right there, for sure, I would have negative flux density. But it's not really obvious to me looking at these pictures whether or not we should come up with positive answers or negative answers. So let's use the theorem and work it out and see what we get. Okay, so this theorem really is awesome. All right, so first of all, let's just plug the things into the theorem. So the first piece here is supposed to be del m del x. So this one is m. So what I'm doing is taking the x partial derivative of this. So this doesn't have any x's in it, so it goes away. Now the x partial derivative of x times y is just going to be y. All right, and then the next piece here is del n del y. So this is n, so this doesn't have any y's in it, so that one goes away. And when I take the y partial derivative of that, I get negative 5. So I mean, look what goes on the inside here. So y minus 5, that's so easy. All right, what about the other one though? So now del n del x. So this one is n. So I'm taking the x partial derivative this time, del n del x. So that goes away, and the x partial derivative of x is just 1. And then what? Minus del m del y. So minus del m del y. So I'm taking the y partial derivative of this. All right, so that y is going to go away and you're just going to be left with x, and then the power rule, you move that up front, you got 10y. So I'm going to work out these integrals. I think it should be really easy, but what I'm saying is look at all the hassle that we have saved ourselves. If I was going to do this using the differential forms, then I would have to parameterize this curve, plug all those parameterizations into this differential form, and parameterize that curve and plug all those parameterizations into this differential form. So that would be 2 parameterizations and 2 differential forms just for flux, and then I have to do it all over again for flow. Look how easy this was to set up. Oh, I should also probably mention the limits of integration here. So I just chose to do dy first, then dx. So if you shoot a laser beam up this way, it enters at y equals x squared, and it exits at y equals the square root of x. And then obviously x goes from 0 to 1. Another thing that makes this easy from a student point of view is that the limits of integration are always the same for both of these problems. So I'm just dying to know the answer. Let me work it out here. So I did this off camera. You guys don't need to see me work out double integrals. It's all just like power rules and stuff here. But I do just want to point out that I got negative, a very small negative numbers for both of these answers. I mean, both of them are less than negative 2. And that actually does match with this picture right here because, so apparently okay, this does actually make sense. So if you look at these arrows, can you see how like over here, there is like quite a lot of large arrows that are fluxing into the region. And then on this part of it, there is quite a bit of it that's fluxing out, but you can see down here, there is just not a lot of outward flux right there. So we got a negative flux here because more liquid is entering the region than exiting the region. So if it would have been positive, that would have meant that more was going out than coming in. And then also the vector field itself would do negative work pushing this thing around. So that means you would have to do some work to push it around. You can see that like right here, we are kind of just barely going against pushing against it. I mean, right here, I think is the most clear example. If we were going counterclockwise down that piece right there, then the vector field would kind of be slowing us down a little bit. So Green's theorem is awesome. It takes like a real hassle of a problem to do that, you have to do a bunch of parameterizations. You got to plug it into differential forms. This time you'd have to break it up into 2 pieces. It really just turns them into some just quick little setup double integrals done.